Hello and welcome to today's webinar, Elevating Everyday Transmission Electron Microscopy with ClearView. Before we get started, I'd like to go through some housekeeping items. During the webinar, if you have any questions at all, please put them into the question box on the GoToWebinar panel. And we will either answer them live after the main content of the webinar or via direct message after we sign off. Okay, I'd like to introduce our speaker today, Fernando Castro. Fernando holds a BS in chemistry from the University of Chicago, a PhD in material science and engineering from Northwestern University, and has been working in the field of electron microscopy for over 10 years. He developed his expertise in TEM and SEM through his research on nanomaterials and lithium-ion battery materials. He is well-versed in many of the key electron microscopy techniques for analyzing material science samples. Fernando joined Gatan after completing his PhD, where he is now an application scientist in charge of supporting imaging and in situ products. Go ahead, Fernando.
Thank you. Hello, everyone. Good morning, good evening, wherever you are in the world. I'm Fernando Castro, application scientist for Gatan, and today I'm very happy to be here with you all in our webinar, Elevating Everyday Transmission Electron Microscopy with ClearView. So our webinar today will give an introduction, an overview of our new ClearView camera, as well as some information on how the camera works, how we can understand different attributes of a detector, and how that all came together to have our brand new scintillator, high-performance scintillator camera product to share with you all today. So, as I mentioned, the ClearView camera is our newest camera. It's a high-performance scintillator camera to elevate your everyday microscopy, hence the title of our webinar. And there's a lot of new things with the camera centered around a brand new sensor running at the core of the camera to help deliver the high sensitivity and speed for demanding experiments, everyday microscopy, imaging, in situ 4D STEM type work that you may be interested in doing with your transmission electron microscope. There's new features both at the sensor level and in the software, DigitalMicrograph, that are implemented to help maximize signal to noise in the data that you acquire, especially for low contrast imaging or diffraction applications like selected area electron diffraction, looking at weak reflections and experiments like that. Its new sensor also helps record the fastest in situ data and 4D STEM data of any scintillator camera that's available currently on the market. And the ClearView camera integrates with what Gatan has recently sort of released, is the easy technology, which allows the ClearView camera to be paired with compatible detectors to acquire multi-dimensional and multimodal experiment data, such as simultaneous 4D STEM and EDS analyses on samples that you may be looking at in the microscope. So I thought it would be useful to go over the ClearView camera and how it fits in the current Gatan imaging portfolio. And normally, I think it's an easy way of describing the different cameras that Gatan offers on this sort of axes, on a low kV and high kV sort of regime on one axis, and a scintillator camera with a CMOS sensor compared to a direct detection CMOS counting camera in the other direction. So if you've been following Gatan and are familiar with our company, we have our Rio camera. That's a low kV scintillator option to run from 80 to 200 kV on a wide variety of microscopes. Our ClearView cameras, our newest cameras, I just mentioned, it was announced last month at the Microscopy and Microanalysis Conference. It's a scintillator camera still. It's our higher kV option. So if you have a 300 kV microscope and are interested in a scintillator camera, the ClearView camera is the one for you. The ClearView replaces our highly successful one-view camera, which many people may be familiar with. So this is the new big brother in that higher kV scintillator camera type offering. And then on the direct detection end, we have two really great cameras. The Metro camera, that's a direct detection counting camera suited really for low kV direct detection work. So doing low dose experiments from 60 to 200 kV, and then the K3 camera or K3AS camera being really designed for 200 and 300 kV work. And of course, we also have our Stella camera, which is a hybrid pixel camera. So pretty different design from ClearView, but I still thought I would mention it's a great camera for diffraction and doing 4D STEM if you're really, really interested in those kinds of applications. But as I already just walked us through the Gatan imaging portfolio, I think there's a lot of terms that we use for describing the different cameras that many people may not be familiar with. So I thought it'd be useful to walk through all the different ways that we can describe a camera and how the design attributes of a camera that you use for electron microscopy can impact its suitability for different applications, different beam intensities, and different kinds of experiments. So as we talk about a detector for your microscope, the first kind of set of descriptors is how the detector is detecting, a photon or an electron. And typically, there's two categories. One is an indirect detection, or also known as a scintillator camera, which is what the ClearView camera is. That refers to the fact that we're not directly detecting electrons coming down the optic axis of the microscope, in comparison to a direct detection camera like the K3, where you are directly detecting those electrons. Now, the other important thing to know about a camera when you are considering its qualities and its suitability for different experiments is the type of sensor technology that it uses. So for the longest time, all the cameras that were used, digital cameras that were used on electron microscope, were CCD-based sensors. And now many people use the term CCD, I think, in a colloquial type fashion to describe just the sensor on a camera in all cases. But nowadays, that's not a really useful way of describing cameras, because there's been a large shift from CCD type sensors to CMOS type sensors, which I'll talk about in more detail in the coming slides. And on top of having a CMOS type sensor, you can also have a hybrid pixel sensor like the Stella camera I just briefly mentioned, or an active pixel sensor, that's what APS stands for, which represents the Metro K3 type cameras that are direct detection cameras. And so there's many more sensor technologies available now than just CCD, and it's useful to understand the difference in many cases. Now, the last sort of consideration for describing a detector, especially as is important for today's webinar, is how you're transferring light through the sensor and turning it into a digital signal. And this is relevant for scintillator cameras or indirect detection cameras, because these cameras are not directly detecting the electrons. There's a process where the electrons are converted into light for the sensor to detect. And the way that light is being transferred affects the sensitivity of the camera and determines whether or not there's any type of artifacts that may be introduced into the image and the data that you acquire with the camera that you're using. So all this goes to say that describing a camera as CCD nowadays doesn't fully describe its performance. It's not the most useful way of understanding the capabilities and the limitations of a camera, because there's many, many, many different options. And today, the ClearView camera, just to outline very directly here on this little plot, it's a scintillator camera with a CMOS sensor, and it uses one-to-one fiber optic coupling to transfer the light from the scintillator to the sensor. Now, if all of that still maybe doesn't sound familiar, hold on to your hats, because in these next couple of slides, I will go through and walk us through some of the differences and key things to know about CMOS sensors and scintillators and all of that. So when we're talking about a CCD versus a CMOS sensor, the sensor type plays a big role in the performance, normally, most importantly, in terms of the frame rates that are achievable with the camera. And that comes from distinct difference in the design between a CCD camera and a CMOS camera in how charge is transferred and read out from a pixel to the computer, where the digital signal is turned into an image for all of us to look at and acquire. So with a CCD camera, once a photon of light hits a pixel in the CCD camera, there's a conversion of photons to electrons and the generation of a charge within a pixel in a CCD sensor, which I'm showing here on the bottom left of this diagram. And now, once you generate charge in a pixel, to generate a digital signal from this charge, the charge has to be physically moved from pixel to pixel to pixel until it reaches a certain part of the sensor where the charge can then be converted into a voltage, into a digital signal, and read out. And so the physical action of having to move the charge around across pixels is what ultimately limited the types of frame rates and acquisition speeds that a CCD sensor could achieve, and that limits its ability for doing high-speed data collection, whether it's in situ or 40 stem or any other type of application that you can think of. CMOS sensors, on the other hand, don't have to do this process of moving charge from a pixel to a certain readout region of the sensor. Each pixel has the electronics required within the design of the pixel to immediately convert that charge into a voltage and read it out into a digital signal much faster. And so by having this difference in the readout process with the CMOS sensor, you can support much higher frame rates, as we will highlight throughout the remainder of this webinar. So higher frame rates support high speed in situ. They support doing things like live drift correction that some people may be familiar with. But one thing that's important to note is that higher frame rates can bring about more total readout noise in data that you acquire, especially if you're integrating a significant amount of frames. So that's something to just keep in mind, and I'll touch on later in the presentation to describe how the ClearView camera has a new approach to minimize the readout noise that's associated with every frame being read out from the sensor. But the idea is that CCD cameras, CMOS cameras, both have inherent advantages and disadvantages. CMOS sensors are much faster. CCD sensors maybe have less total readout noise that are introduced into the image. And the idea is about optimizing trade-offs between the different cameras to hit different performances. And nowadays, I think most of the cameras that are scintillator cameras that are available on the market are CMOS-based designs, which have been chosen to really take advantage of a high frame rate camera for recording video or allowing more advanced data processing compared to what's possible with a CCD camera. Now, that's the difference between a CCD and a CMOS sensor and how it plays out into the camera design and performance. The other aspect is the scintillator aspect of it, the detection mechanism of the camera. And so I mentioned that scintillator cameras are also referred to as indirect detection cameras, because the actual CMOS sensor, or CCD sensor, but in this case for the ClearView it's a CMOS sensor, these sensors are not directly detecting the electrons that are coming from the microscope. What happens is that the electrons from the microscope come and hit the top of the sensor assembly on the camera. And at the top of the sensor assembly is this purple scintillator region. Now, the scintillator is an organic phosphor, and when an electron hits the scintillating layer, it excites light, and that light then is what is detected by the CMOS sensor. Now, in order to detect that light at the sensor level, there needs to be a coupling mechanism of the light from the scintillator into the CMOS. And that's another important aspect that I sort of introduced 1 or 2 slides ago about whether you have fiber optic coupling or lens coupling, etc. But the idea is that you're generating light to detect in the sensor. It's a very good way of working with high doses on the camera, but at times, especially in comparison with a direct detection camera, there is a lack of sensitivity for, especially in the case of low dose experiments, that comes from sometimes inefficient light transfer just from the scintillator to the CMOS sensor. So that's one advantage of having a direct detection type camera, is that you don't have this scintillating layer and this light transfer process to worry about, and that improves the sensitivity of direct detection cameras. Nevertheless, scintillator cameras still are very good cameras for everyday microscopy, as we mentioned at the top of the presentation. Now, as we move the light from the sensor, or sorry, from the scintillator down to the sensor, there's a couple of different strategies for having this coupling of light. The earliest designs, I think, were primarily lens coupling devices. So there are actual optical lenses in the camera system that would take the light generated from the scintillator and focus it down onto your sensor. Back in the day, also, most sensors were CCD-based sensors, and so that's what this diagram shows. Now, this was a relatively inexpensive way of having this light coupling between the scintillator and the sensor, but it has all the disadvantages that come from using a lens to focus light. So you can get vignetting in your image, you introduce aberrations like chromatic aberration that comes from having the lens. There can be light loss and other distortions that happen in the image, especially when you're at high magnifications. Using fiber optic coupling instead, you use an optical fiber to link the scintillator directly to the CCD sensor or CMOS sensor in this case, and you get better light transfer and remove any type of lens related distortion from the image, like some type of chromatic aberration like vignetting, which can affect your data across a wide range of magnifications. Now, the way that plays into the image quality that you're able to acquire with a camera, comes down to the sharpness of the detail that you're able to see a lot of the times, along with having vignetting in the lens coupling case, where you would see a dark edge at the border of the image. But if you draw your attention to the sort of feature being circled or outlined by this black box in the renal sample, you'll see that with a lens coupled system, you don't have as sharp of features and contrast in this small region of the sample compared to a fiber optic coupled image where there's much higher detail that's available that comes from not having any lens related distortions. And so the ClearView camera, all of the scintillator cameras that Gatan offers have this fiber optic coupled design, specifically 1-to-1 fiber optic coupling, which just means that the diameter of the optical fiber is the same at the scintillator end as it is at the sensor end. So that gives you the best light transfer and removes any lens related distortions from the image. So now that we've walked through very quickly about what's the type of camera design attributes behind the camera, let's dive into a little bit more specifically about the camera, all the things that I can do with this new redesigned CMOS sensor. Now, the big thing about the camera, the easiest thing to talk about in its performance first is that it's a 4K by 4K camera, so a 16 megapixel camera. and it can acquire data at up to 50 frames per second at 4K by 4K images, the image size. One really nice thing about the camera that I'll talk about more in depth is that it has these HDR, or high dynamic range sensor readout. It's a sensor level sort of readout scheme that improves the dynamic range. It's super useful for diffraction experiments that you may want to do with the camera. And because the ClearView camera is the successor of the OneView camera, and it uses DigitalMicrograph to control the camera, we have established camera workflows within the DigitalMicrograph software that we continue to leverage to make experienced users and even new users work with the camera very efficiently and with a very low learning curve. So I mentioned that the ClearView camera, it's 4K by 4K camera. It can acquire data at that image size at 50 frames per second. So this is twice the speed of OneView. It's a pretty healthy performance boost. And what I'm showing here at the top are some images of this lithium-ion battery material that's collected by collaborators at the University of Illinois at Chicago, showing some really nice high-resolution TM lattice structure of this manganate material. With the ClearView camera, you can operate the camera in its standard form from 80 to 300 kV. So that's why I sort of described it as the higher end or higher kV range camera that's offered by Gatan. And as I already talked about, it uses one-to-one fiber optic coupling from the scintillator down to the sensor to have a high efficiency signal transfer. Now, the HDR, the next thing about the sensor is that it has these HDR readouts that are new to the camera in comparison to the OneView camera. So with ClearView's HDR sensor readouts, it improves the dynamic range. It makes it really good for electron diffraction, whether you're doing 4D STEM or you're doing selected area electron diffraction. It's designed to be free from artifacts associated with CCD sensors. So that would be blooming of high intensity regions of the image, especially for diffraction patterns, and has minimal artifacts associated with CMOS sensors like crosstalk, which some people may be familiar with. And of course, people always ask, can you do diffraction data acquisition with a camera without a beam stop, so you don't have that big beam stop blocking the center of the beam and making it harder to do some type of analysis? You can. With this camera, you can use the camera to acquire data with or without a beam stop, no problem. So a lot of times people are interested in knowing a little bit more about what is the HDR sensor readout, what's going on in the camera, and how is that affecting the image generation or the data coming off of the camera. So we have our little pixel here on a camera. The pixels read out at a 12-bit depth image, and each pixel, depending on how much intensity it has, whether it has a low intensity signal or it has a high intensity signal, can use one of two different readout channels that each pixel will have to process a low intensity signal and a high intensity signal differently. So as if you read out either the low intensity signal or the high intensity signal, you can apply all the standard processing that happens in the camera. With the camera, there's a linearity correction, there's a dark subtraction, there's a gain normalization that happens. But you can tune the processing steps to be better optimized for low intensity signals and for high intensity signals. And then at the end, combine the two signals from the pixel into one signal, which is the HDR signal. So the advantage of combining these two images, or these two signal channels into one HDR signal, means that you can go from a 12-bit image to a 16-bit image. So that improves the dynamic range that's capable of the data coming off the camera. And if you sum together more and more frames into a final acquisition, you can extend the dynamic range in terms of bit depth beyond the 16-bit bit depth limit. So all this to say is that with the HDR scheme, you can output data at 16-bit depth, and it saves it now standard to a .dm4 format. That's a DigitalMicrograph format that comes in the 32-bit depth data format. So Now that we sort of talked about two of the big things going on with the sensor, I had mentioned that we are using DigitalMicrograph just like with the OneView or the Rio camera to control the camera operation and acquire data. So this is the palette, as we refer to it, the ClearView camera user interface within DigitalMicrograph. And if you've used a OneView camera, a Rio, or even a Metro camera, it should look very familiar. When you go to set up your experiment, you have the ability to choose the image size. So that's what you see here, a 4K by 4K image, a bin by 2 image, which is a 2K by 2K image size, or a bin by 4 image, which is a 1K by 1K image size. You can set your view time just like you normally would. You set your capture exposure time just like you normally would. So it's really easy to get going with the camera right away to acquire your data. Now, I'm sure you noticed there's two more things here in the camera UI, and these are the two really, I think, great features that enable high signal to noise and high spatial resolution data acquisition. The first one is drift correction, live drift correction, which was a feature both on our OneView and Rio cameras and comes back to the ClearView camera for everyone. The second one is our frame control button here, which allows you to adjust the camera frame rate actually to help maximize the signal to noise in the imaging and diffraction data that you acquire. So the camera comes with live drift correction, and this as you acquire single images. And this, of course, can be very useful because all microscopes have some level of drift with them. If the stage is unstable, if you just move the stage, if you're applying an in-situ stimulus or anything like that, acquiring long exposures without drift correction can give a very blurry image very quickly. Now, by having the live drift correction enabled with the camera, super easy to do. You just click that checkbox that we saw in the previous slide, and you'll be able to acquire drift corrected data with much sharper detail. It removes any of the blurring from the image, and you can use the ClearView camera to acquire up to 30 seconds of drift corrected data. So if you are doing a low dose type experiment and you need to acquire an image for a rather long time, this live drift correction feature is really, really, really great. But the new feature to the ClearView camera, especially compared to OneView for all the people who have our experience with the OneView, is the frame control mode. And so, as I mentioned already, the frame control mode is a manner of directly controlling the frame exposure time, or put in other words, the frame rate of the camera at any imaging condition. And so the idea is, as I mentioned at the start, with a CMOS camera, you're capable of having very, very high frame rates. But if you acquire an image at a high frame rate and integrate a high number of frames, there's a certain amount of noise, readout noise, that's intrinsic to reading out the data of the sensor. And the more frames you integrate, the higher your noise floor will be in the data that you acquire. And this is true for any camera. There's readout noise associated with any type of digital readout process, whether it's a direct detection camera or an indirect detection camera. And so what I'm showing here is a diffraction pattern just of gold. So we're seeing gold diffraction rings. And this is an image that was acquired at 200 frames per second. So we're integrating 200 frames per second. There's 200 essentially units of read noise that are being integrated into the image every second. And if we look at the radial intensity distribution on the left of this diffraction pattern, clearly you can see a lot of rings, and you can see that way out in the image, there is a significant amount of counts that come from having this sort of background noise that's integrated into the image. Now, if you use the frame control feature of the ClearView camera, you can decrease the frame rate to say 100 frames per second. And now I think you can see both in the diffraction pattern and in the radial intensity distribution, there's a decrease in the background level of the noise that you're seeing. The image itself looks darker in the background, which is what we want to see. And the radial intensity distribution, especially all the way on the right-hand side of the plot, which is the furthest away from the center of the diffraction pattern, you'll see that there's a decrease in the counts there, in the sort of noise floor of the image. And if we use the frame control to go even further to something like 50 frames per second, now you really start seeing a significant decrease in the background noise of the image. And all of this is great, but really where this feature really starts to stand out is if you look at, for example, the features on the radial intensity distribution at about the 700 pixel index, you'll see that at 50 frames per second, which is the green line, there's a lot more detail that you can resolve in the essentially radial intensity distribution than you can if you are acquiring data at 200 frames per second. So by using this frame control method and decreasing the noise floor from the data, you can start to see new things in your data that you wouldn't be able to without using this frame control mode. And so I think that this is one of the best modes of the camera, and it's going to have a lot of utility for a wide range of applications, both diffraction and also imaging, here as I show on this next slide. So here we have, I'm showing an image captured at 50 frames per second. It's a 2-second total exposure. So there's 100 frames that have been integrated together to give you this nice image of a semiconductor sample. Now, if you focus in on, say, this region here, and we blow it up in the image, you can see that because the ClearView is a 4K by 4K camera, you can zoom in really far and still see a lot of detail in a smaller region of the sample. And this is what the data looks like at 50 frames per second for a 2-second total acquisition. You can see these different features, but when you use the frame control mode to decrease the frame rate down to, say, 1 frame per second and have 2 total frames integrated, there's a big difference in the essentially noise levels of the image when you compare the middle image at 50 frames per second and the right image at 1 frame per second. And if we start looking a little more in detail at some features, maybe people are interested, not necessarily maybe in this sample, but you can imagine that if you were trying to resolve some type of small interface in a sample, or look at 2 different regions that had very similar contrast, the ability to use the frame control to reduce the background levels of noise in the image and improve your ability to see these low contrast image details can be, very, very significant. So I love this feature. The last example I'll just show you about the frame control is applying it to a diffraction pattern, even more so than we did in the first example. So the previous diffraction experiment showed what a pattern might look like at 50 frames per second. So this is a silicon diffraction pattern. It's just a substrate of the sample that we were looking at in the previous slide. And I acquired it 4 frame per second image for 1 second total acquisition. So that's 4 frames that we've integrated together. And this is what our diffraction pattern looks like. If I stretch the contrast actually here, you can see that there's a lot more detail here in the sample than we may have thought by just looking at it. And if we dive even deeper into see what we can see with this pattern, for example, I'll take a look at this region here that I've outlined in the blue box, blow that up, and if we look at the diffraction spots here, you'll see that there's, I think, 3 spots that are really interesting to kind of look at. Here's one that I've circled and labeled 1. You might not think there's any intensity there, and it might be really hard to see, but you'll see in the line profile, which I'll show next, that there's actually some data that we can acquire from there. So here's spot 2, here's spot 3. If we draw a line profile across this row of spots, here's what the line profile looks like. So I'm showing here in the intensities, it's one line profile, but sort of broken into 2 different Y scales to show the range of values that you can acquire in the, or range of intensities of the spots that are shown in the image. So you can see this spot number 1 has as few as 1 or 200 counts in total intensity when in the line plot region that we're using, and other spots in the line profile can have over 250,000 counts in these diffracted spots. So it's showing the the type of dynamic range of the signal intensities that you can acquire by the camera. But I think it's also really showing your ability to resolve weak spots with the camera, like this spot number 1, or even the spot number 2, that you wouldn't be able to see without the frame control mode if we were just integrating the maximum number of frames that we could possibly to acquire the data. You'd have more background noise, and that would start to obfuscate some of these weaker diffraction spots. So on top of that, once you figure out what's a good frame rate, minimization of the background noise, you can then just extend your capture time to improve the signal that you get total into each diffraction spot. And that's how we can maximize the signal to noise in our imaging data and also our diffraction data. And with the camera, you can acquire frame exposures as long as 30 seconds, meaning that your frame rate can be as low as 1/30th of a frame per second. Now, the last thing I'll just mention about the camera is the true line feature. This is something that's really useful. It's an optional feature that comes with the camera, but allows you to do essentially an arbitrary 360-degree rotation of your image on the left to get a desired orientation on the right. So I know here it kind of just looks like I just did a 90-degree rotation really easily, but it's actually was like an 86-degree rotation. And it's something that you can very easily set up with this true line feature. The orientation is maintained throughout your entire electron microscopy session, and people in the semiconductor industry, or sometimes people in the pathology industry who are looking at certain structures and want to see in particular orientations, they really like this feature. Now, that was all of the sort of imaging and diffraction kind of static data acquisition with the ClearView camera, but the ClearView camera is also a great camera for in situ and 4D STEM data collection. So the camera at its fastest frame rate can run up to 1600 frames per second using a combination of binning and sub-area readout, which I'll talk about in the coming slides. But this makes it a really great camera for looking at super fast, dynamic phenomena in an in situ reaction, or rapidly acquiring a large area 4D STEM data set with the camera here. So when you have the in situ version of the camera, you'll have a different type of palette control, user interface control when the camera is in situ mode. So you'll still have your binning options to choose your image size. And when you use the image binning, you improve the frame rate by up to 4 times. And when you have the in situ version of the camera, you also have these abilities to have a sub-area sensor readout, which can improve your frame rate 8 times. And the combination of these two is what lets you go up to 1600 frames per second at a 256 by 256 image size. Now, you can combine either of those binnings and sub areas to get many different frame rates, and that's kind of what this table is showing here. All the different image sizes and frame rates, and importantly also data rates that come off the camera at different combinations of binning and sub-area readouts. Now, the one thing that's important to note is that when you have different sub-area readouts, you will affect the field of view of the camera. So if you have full area, you'll see this whole image that I'm showing here on the right. At half area, you'll double the frame rate at any binning level, but half the field of view by taking the center half of the sensor that's only read out. That continues with 1/4 and then 1/8. So with 1/8 area, you can go very, very fast, but you do have a smaller field of view. This may be still suitable for an in situ reaction, maybe if you don't care about having a really large field of view, but it also makes it really, really good for 4D STEM in this sense, because a 256 by 256 diffraction pattern often suffices, and you should leverage the speed in that case to acquire your data very easily. Now, just to give you an idea of what kind of speeds all of these different frame rates are, as I mentioned, the ClearView at 4K by 4K gives you 50 frames per second. And so here I'm showing a demonstration. It's very simple. It's a 10 micron stage movement that I asked the microscope to move by itself. So it happens very fast. And if I play the data, you'll see that you can see the stage move pretty quickly at 50 frames per second. And I think it gives a good live view experience. It makes the camera really good for just navigating around in your sample, using the wobbler to do different microscope alignments. But if we slow it down to 1/10 speed, I think you can see clearly in the image that at this frame rate, we can't quite capture clearly the action that's going on. There's blurring in the image in our cross-grading sample here that I'm using for this demonstration. But if you bin the image to bin by 2, so you have a 2K by 2K image, you get boosted automatically to 200 frames per second very, very easily without sacrificing your field of view. And at the same 1/10 speed, you can now very clearly see this very fast 10 micron stage movement and see all of the details. So it's really, really easy with the camera to start capturing rapid in situ movement or phenomena that you may be interested in recording. And of course, if you wanted to, you can go 1600 frames per second and still capture in situ data as I'm showing here. Now I'll point out that this is at 1/100th speed. We can still see things pretty clearly. And I'm only showing part of the video because 1/100th speed over just a few seconds at 1600 frames per second would take a few minutes to show that whole data set. But there's something important that I think is always that it's really key to understand about how the camera works with these different binning and sub-area combinations when you're interested in analyzing your sample. And that has to do with your field of view and your ability to detect high spatial frequency information. So if you use binning, you don't affect your field of view. Here I'm showing the field of view at bin by 1 and the full sub-area readout of our test sample here and an FFT of what it looks like. So this is gold. You can very clearly see these 2 gold rings at this magnification that we've chosen. But if we use bin by 2, what's happening is that you're effectively increasing your pixel size. And so although you don't change your field of view, the increased pixel size affects the Nyquist frequency, or just to put in simpler terms, by increasing your pixel size, you're decreasing your ability to see high resolution spatial information through the FFT at the same given magnification. And so going to bin by 4 shows us even further. In the FFT, now we can't make out the 2 gold rings in the FFT at the same magnification because now our pixel size is too large. Fortunately, all you have to do is change your magnification and zoom in a little bit, and then you should be able to resolve those rings again. But now if you use a sub-area readout, instead, if we look at the image, field of view, and the FFT again, as we decrease the sub-area readout without changing the binning, you'll change your field of view, but you won't be changing your pixel size. So you're not changing your ability to resolve high resolution information through the FFT. So even if you go all the way down to 1/8 sub-area readout, you can still resolve these 2 gold rings that we saw at the full image size there. And so we've been given the controls to the user here to have both binning and sub-area readouts for their in-situ data set acquisitions. So you have the most control over picking not only the frame rate and the data rate that you want to have for your in-situ data, but also to set up and experiment with magnification control and the field of view and the pixel size that you want to be able to optimize the temporal resolution and also your ability to have high spatial resolution in the data that you acquire. So that's a very quick overview of the binning and sub-area readout modes that we use for acquiring data. And acquiring data is only the first step in working with an in-situ data set, right? So we have controls within DigitalMicrograph for using the image binning, the sub-area readout, the frame rate to set up the camera for acquiring data. We also have features like lookback, which is a video buffer that records a certain amount of time and then in a ring buffer. So the idea behind that is you don't have to record any data until you see something exciting happen in your sample when you introduce the in-situ stimulus. And if you have the look back on, the data will start recording the moment you hit record and include up to 15 seconds looking back in time that's appended to the start of your data set. So you don't miss the start of your reaction. Many people also sometimes want to acquire really, really long videos. So do have an in-situ experiment that takes 1 or 2 or even more hours, and they want to record the whole process. And that 4K by 4K, 50 frames per second, that will be terabytes and terabytes of data that you acquire. So we have this new time-lapse feature on the ClearView camera, but also all our in-situ cameras that allows you to save data at a longer interval of time or number of frames to easily acquire these really long videos that you may want to. Now with the ClearView camera and all in-situ data cameras, in-situ cameras from Gatan, all of the data as you're recording it is automatically saved to the disk on the computer. And so this is done so if something, horrendously wrong happens for some reason during your experiment, you're not losing any of that data. It's already been saved onto the computer. And something that's really useful about the camera data that comes from the ClearView and other in-situ cameras is that the camera data, if you're working with a third-party in-situ holder that's supported or Gatan in-situ holder that's supported, the metadata from the holder can be read into DigitalMicrograph and synchronized with the camera data and played back together to help with your analysis. And so that's a really useful feature when you're working with in-situ data here. So what I'm showing here, for example, is this magnesium chloride salt that is at 500 C. And when you put the beam on it, you start seeing degradation. There's these bubbles that happen in the film. And what I'm showing here is that you have some drift in the image in the direction that I'm showing. And you also have this playback marker on the right-hand side, which is the holder metadata sort of plot that plays back synchronized with the data, the video data that you collected with the camera. And so there's a bunch of different types of holder metadata based on which holder you're using that can be saved alongside with the data, like the temperature that you're using or target temperature, different currents or resistances with the holder, which can be really useful for always understanding what the exact experimental conditions are during certain moments of the video data. And DigitalMicrograph has all the tools to help process that data from the moment you acquire it to the moment you need to export it and put it into a presentation to share. So we have our in-situ player and in-situ editor tools, which I'm showing here on the right. The player is used to play back your data in a synchronized manner from both the camera and the in-situ holder if you set the experiment up that way. You can highlight the result on your video very easily by adjusting the region of interest or the field of view of the video that we're showing to show only the most interesting part or one specific particle you may be looking at. You have the ability to adjust the start and end points of the video and crop it in time. You can do things like bin the image or combine together many frames to improve the signal to noise in the video. And then one really exciting thing that has been in DigitalMicrograph for a while, but has been revamped with the new version of DigitalMicrograph that will be coming with the ClearView camera is the ability to do drift correction post-processing on the video data that you acquire here, which I'll show more in depth in the next slide. We've always had the ability to apply filters for more advanced processing. That's still here in the newest versions of the software. And then when you have your video all set up, you can export it to an MP4 video or a Gatan in-situ data set. You can do things like export one frame to a TIFF or a DM4 file, or say sum together the whole video into one final image. There's many, many export options. And the great thing about working within the in-situ editor and in-situ player tools is that any processing you do on the video is non-destructive. So if you do adjust, say, the start and end point, and you decide you don't like it, you can go readjust it, or you can turn it off entirely by just turning off the checkbox that we see here in the user interface. And it really helps you manage the data size of the in-situ data before you export the data. Because with the camera, it's very easy to acquire hundreds of gigabytes of data in a single session. And then with these tools, by using the spatial editing and the temporal editing features of the editor, it's really easy to turn 100 gigabytes into 1 gigabyte or less video that is very easy to put into a PowerPoint presentation, as we see here. So just to show a little more in depth of how we would process this data, this is the same video. We could play it back. On the left is the video. On the right is the metadata that's being played back in a synchronized manner in DigitalMicrograph. If we wanted to drift correct this data because there was some drift that we observed, we use this spatial alignment tool within the newest version of DigitalMicrograph to generate this plot here on the bottom. This is the drift plot, essentially, of the video that is calculated by the spatial alignment tool. And then this drift plot can be applied directly to the video to give you a really, really nicely drift-corrected data that you can then crop in the region of interest and the duration and export it into an MP4 with annotation and put it into a PowerPoint presentation today for everyone. Now, the last thing I want to talk about very quickly is your ability to do 40 stem data acquisition with the ClearView camera. So when you have the ClearView camera and you pair it with the StemX system from Gatan, that enables what's called hardware-synchronized data acquisition. And all that really means is that you can fully leverage the maximum speed, the maximum frame rate of the camera and acquire 40 stem data at up to 1600 frames per second at that 256 by 256 image size to do things like strain mapping, virtual aperture analysis of the material, differential phase contrast. These are things that are built into DigitalMicrograph, and then you can leverage things like Python scripts directly within DigitalMicrograph as well to do additional types of analysis. And by using the StemX system, you get the advantage of over a traditional workflow where without the pairing of the camera with StemX, you'll have multiple computers and places where you need to do the experiment setup and the data acquisition. You need to take that data, put into a different computer to actually look at the data, analyze it, and figure out if the data is good or not before going back to the original setup to re-optimize the experiment, recollect some data, and then finally transferring it somewhere else for long-term storage or management or further processing to put into a paper or a presentation. And all of these different stations that many people work at reduces the efficiency and the time to results, or increases the time to results compared to the DigitalMicrograph workflow, where you use the DigitalMicrograph software to help set up the microscope, to do the data acquisition with the camera, to do some very quick data mining and processing directly in DigitalMicrograph, either within with the built-in tools, with some Python scripts that people may be interested in, until you have to go and export the data here and manage it in the long term. So this is a very quick data set example of the of using virtual apertures on data that was collected with the ClearView camera. So this is our semiconductor sample again that I showed earlier in the presentation. And this is a 256 by 256 scan size. So it's a pretty large scan. And the diffraction image, or the image off the sensor that we're using again, is 256 by 256. So the camera is running at 1600 frames per second. And we can acquire this 256 by 256 scan area in as little as 41 seconds. And so that's really, really, really fast for especially a scintillator camera. And I think it's a huge advantage for the ClearView camera over the OneView, for example, if you're familiar using that camera. So within DigitalMicrograph, you can select different parts of the 40 stem scan area, investigate the diffraction disks here, and then select different features within the diffraction patterns to act as a virtual aperture and see the different diffraction informations spatially in the original map that we're showing here on the right. And then you can take those maps and combine them into very easily within DigitalMicrograph into a RGB image to give you some fun mapping of structural information, diffraction information in space at essentially any different type of condition or spot in the diffraction pattern that you may be interested in analyzing there. So the workflow is very easy. And the last thing I just want to mention about working with 40 stem data in DigitalMicrograph is that in these new versions of DigitalMicrograph, you can now start doing very fast 40 stem acquisition. And if you pair the ClearView camera with a compatible EDS detector, you can do simultaneous 40 stem and EDS data acquisition directly within DigitalMicrograph. And DigitalMicrograph will link the two data sets and help you analyze the two data sets simultaneously, so you can have both elemental information and structural information and have it mapped out over a large area of your sample. So that's really the sort of bleeding edge of where the technology is going and how these cameras can be leveraged together with other hardware on your microscope to give you more complete data sets for a wide variety of analyses. So this is the end of my presentation here. The ClearView camera, I think, is a really great camera. It's a big step forward, especially over the OneView camera, and I think will prove to be excellent for in situ data, doing diffraction with the frame control, 4D STEM data, really well suited for the wide variety of microscopy applications that people are interested in doing nowadays. So with that, thank you all. I'll remind you all that you can submit questions through the question pane in the GoToWebinar interface. And if we don't get to your questions, we'll answer them offline. The webinar recording will be posted within the next 7 business days to our website, which is www.gatan.com. So thank you all. And now we can open it to questions.
Thank you so much, Fernando. We are running very short on time, but I'd like to get at least 1 or 2 questions answered. The first one is, how variable is the sensor readout frame rate with frame control?
Yeah, so I mentioned that there is, the frame control lets you adjust the frame rate. So when you have it enabled, the maximum frame rate that you can use is determined by the binning or the sub area readout mode that you've chosen for the camera. So that sets the maximum frame rate that you can use. But the minimum frame rate you can use, or the slowest frame rate you can use, is 1/30th of a frame per second. So, and that's at any binning and sub area readout combination. So you can also essentially acquire 1 single frame readout that's exposed for 30 seconds and then read out. And then you can also choose any frame rate between that upper and lower limit. There isn't a set of frame rate options that you can use. It's very, very variable.
Okay, thank you very much. And we'll finish off with this last question. It's kind of a 2-part question. How exactly does the ClearView compare to the OneView camera?
Yeah, so I think that there's 3 really big improvements on the ClearView over the OneView camera that I highlighted in the presentation, but I guess I'll summarize here again. One big thing that the ClearView camera can do, which the OneView didn't, was this have this frame control mode, which lets you really optimize the signal to noise in the image. The second thing is having the ClearView has this HDR readout on the sensor to improve the dynamic range. So the ClearView dynamic range will be much better than the OneView dynamic range. And then, of course, the maximum frame rate on the ClearView is much higher than the OneView, and that makes it better for, as I was showing, 4D STEM, but also in situ. Now, there's other things like that I think are more minor, like the ClearView camera, the DQE, or in other words, the sensitivity of the camera is slightly higher than the OneView, and the resistance to certain artifacts that you see in diffraction, like crosstalk, is much better with ClearView over OneView. But overall, I think like the frame control, the HDR readout, and the frame rate options are the big differences and advantages over the OneView camera.
Okay, and with that, is it possible to upgrade a OneView camera to become a ClearView?
Well, so it's not physically possible to upgrade, like to make changes to a OneView camera and turn it into a ClearView. They're 2 different cameras because they have different sensors and different internals. But the ClearView camera was designed to very easily swap in for a OneView camera. So the ClearView has the same footprint and the same TEM configuration compatibility as the OneView camera. So it can be a direct 1-to-1 replacement really easy. You can even reuse the OneView computer to use the ClearView computer. So if you have a OneView and you were interested in upgrading, it's very easy to do so.
Okay. Last one before we go. Are all binning and sub area readout functions available without the IS option?
So the sub-area readouts are only available with the IS option. The binning options are available for the base camera, as we call it, and also the in-situ version. But if you're interested in having the maximum frame rate and having the control of these sub-area readouts, that requires the in-situ version of the camera.
Excellent. And we are out of time. To everybody on the call, just know that you will be getting a follow-up email today asking if you have any further questions, if you think of something later, or if you didn't get the chance to put it into the questions panel. And then in about 7 business days, if not earlier, you will also receive a copy of the recording to your email address. Thank you so much for your time, Fernando, and thank you everybody for attending.
Thank you, everyone.